Hello and welcome back to numerical analysis. So today what we're going to be talking about are nonlinear equations, and this is the start of, say, the second half of the class. So thus far we've talked about approximating functions with polynomials using Taylor polynomials, interpolation, and Bernstein polynomials. Then we use the interpolation theory in order to give us guidance in establishing differentiation and integration results. So we talked about, say, symmetric differentiation routines. We talked about asymmetric ones, which don't converge quite as fast, and how to achieve these by using interpolating polynomials. After that, we went ahead and established things like the trapezoid rule and the Simpson's rule using interpolating polynomials, and we showed that those converge fairly quickly. So, what are we doing today? Well, today we're making a shift, and we're moving to talk about nonlinear equations. And this is one of the central aspects to numerical analysis, and it's something you have to do quite a lot, is solving equations. When you're solving linear equations, you can just use the tools of linear algebra. You have a matrix equation times a vector is equal to, say, b, so ax plus is equal to b, and then as long as the matrix A is invertible, you can invert it, and ta-da, you're done. So solving linear equations isn't bad, and systems of linear equations is just matrix inversion. And so the question is, what do you do when you're confronted with something like a nonlinear equation? Say x squared is equal to b. Now that's fairly obvious. You just take a square root. But we can make that more complicated. We can have, say, sine of x is equal to tangent of x plus 1. And then what do you do? There's a lot less obvious things to do there. You can't use, say, the inverse of sine because, well, x is trapped underneath tangent as well. And you might be able to get away with coming up with some sort of trig identity with sine and tangent, maybe, in order to solve it. Nothing comes to mind right away. But, there are possibilities. But on the other hand, we have some tools that we developed back in Calculus 1. So Calculus 1, one of the big applications that we saw for differentiation was Newton's method. Newton's method it takes a nonlinear equation, f of x, and we're trying to find its roots or its zeros. And generally that's what we're going to do, is we're going to change every nonlinear equation that we have into an equation that involves finding the root of a nonlinear function. So even if we have something like, say sine of x is equal to 1, we can change that to being in the form of f of x is equal to 0 by just shifting the 1 over. So it's sine of x minus 1 is equal to 0, and that's an equivalent equation. And so then the goal is to, say, find exactly where that happens. Obviously, pi over 2 is an answer. But basically what we're going to do is we're going to have general nonlinear equations, and we're going to use Newton's method, at least this round. The next couple lectures are going to introduce other methods, but here, this is a nice place to start because we already know what Newton's method is. You basically take a function, f of x, and you're trying to find its zero. Well, you make a guess, say xn, or x naught, and then you want to find out what your next guess should be. Well, so you change the problem from being a nonlinear problem to a linear problem, iteration of linear problems, where basically you take that x naught and you look at the function at that point, and you take the linearization of that function at that point. And then instead of solving f of x is equal to 0, you solve the L of x equals 0, where L is that linearization. And so you've changed the problem from being a nonlinear problem to a collection of linear problems, where basically each time you solve for the zero of that linear equation, you get a new guess, and then hopefully that's closer. Now, it's not always going to be closer. There are some problems that you run into with, say, Newton's method, and one of those problems is that sometimes you can run into a cycle. And so we'll talk about that a little bit too. But what we really like to know is, how do we know when we're going to converge? And so that's going to come down to some conditions on the second derivative and the first derivative. And so we're going to assume that the function is, say, twice differentiable. And on making that assumption, we can use the mean value theorem, just like we do in everything else in numerical analysis. And it gives us a way of coming up with a condition that is going to give us convergence. Basically, what this condition is going to say is that the difference between the nth iterated guess and the point that we're looking for is going to be less than the previous guess, the difference between the previous guess and the actual value times some quantity less than 1. And so that means that you're basically shrinking each time each iteration is shrinking your error, and so hopefully you can leverage that in order to get convergence, and that's what we're going to do. Okay, so this is Nonlinear Equations, and it should be a lot of fun. And yeah, let's go ahead and get started. So today we're going to talk about nonlinear equations. Nonlinear equations, they come up a lot, and here are two equations that they end up coming up with. One is going to be in, say, solving or finding an estimate for the cube root of 2, and that's going to be related to this function f of x is equal to, say, x cubed minus 2. And so then we know that this is going to give us f of cubed root of 2 should be equal to 0. And so if we can find a way of estimating the root of f, or this particular root of f, then that'll give us the cubed root of 2. So here we're trying to solve the equation f of alpha is equal to 0. And that is, generally speaking, what we're trying to do. This function is nonlinear, so it's not ax plus b, so it becomes difficult to solve in some cases. A subtle place where this comes up a lot is in the solution of differential equations. I am just going to sketch out sort of proof here, or maybe I'll do it and fast forward it, or maybe I won't. I don't know. We'll see in like 3 seconds. But if you come and look at this differential equation, this here is actually separable. So I can rewrite this as, say, dy times y times e to the minus y is, or sorry, times e to the y is equal to e to the minus x dx. And then we can end up solving it. On the left-hand side, we'd have to end up using integration by parts. So it's going to be e to the y dy, and have u is equal to y, which gives us du is equal to dy, and dv is equal to e to the y dy, which gives us v is equal to e to the y. Right, so uv would be y e to the y, and then minus the integral of v du, and so v is e to the y dy, and ultimately this gives us y e to the y minus e to the y. Right. On the other hand, we would have something on the other side. We'd end up just integrating e to the minus x, and so ultimately what this gives us is y times e to the y minus e to the y is equal to minus e to the minus x plus some constant. If we want to figure out what the constant is, we just plug in 0 for x and y, and we end up getting this. We have 0 minus, say, 1 is equal to minus 1 plus c, which tells us that c is equal to 0. Okay, so now we're left with this. We have a function that we're trying to find, which is y, but it's trapped here. So we want to figure out how do we find y. So let's go ahead and continue this on the next page, and we'll talk about it. So we have this, and we want to solve for y. Which is actually a function of x. And so, but it's not possible algebraically. So we have to use some sort of numerical method in order to do that. What is this numerical method? Well, what we're going to do is we're going to fix some, say x equals x naught, so let's just say 2. This is, you can replace 2 with any value you want to find. So now we can say, what is y of 2? Well, then that'll be whatever you get when you solve this. E to the y is equal to minus e to the minus 2. And so over here we can think of y as being sort of y of x, but we're trying to solve this equation. So we solve this to find y of 2. Well, we can rewrite this like this, and it becomes y times e to the y minus e to the y plus e to the minus 2 is equal to 0. And so we can reframe this whole problem as f of y is equal to 0. And so this would tell us, so finding the value, say, of y that makes it 0, gives us a candidate for y of 2. Okay, so there might actually be more than one solution for a particular equation. So for instance, if it ended up being just say y squared minus 2, well, we'd have plus or minus square root of 2, right? So we might end up having multiple solutions here, but there are certain things that you can do to make guarantees that you're going to get a unique solution. I think here you end up getting a unique solution because you basically write that it's e to the y times y minus 1, and I think that is strictly increasing as far as y is concerned. I'd have to double check that though. But yeah, so you know, if your function f is strictly increasing, then you're guaranteed that you find it. In any case, so then this has also set up this equation where we're trying to find something like this. So the general problem is that we want to find a 0 or root for a function f that is nonlinear. Now, why do we care about nonlinear? Well, linear equations we can solve just with like what we learned back in high school. Here we're trying to do something a little bit more complicated, and so we might have, you know, f involves sines, exponentials, cubes, cubed roots, you know, pretty much anything that you can think of, and we're trying to find some conditions on f that would allow us to implement some sort of routine to find a root. And so the first of these kind of routines is something you've already seen, and this comes straight out of calculus. And so so the first approach we're going to do, and we're going to do at least 2 approaches in this class. Here we're going to be talking about Newton's method, but we'll also talk about the secant method, and if I have time, also we'll address some other searching methods. So let's go ahead and get started. All right, so let's go ahead and talk about Newton's method. So the general idea of Newton's method is that you replace a function, say this is f of x, and we're going to replace it with a secant line at a point. So we always start with a guess. Say x naught. And so here, put that in red, this would be our x naught. Right? So, and then what do? We are going to, instead of finding a root for f, we look for a root of a linearization of f. Right, so what I mean by linearization? Well, we're going to take a tangent line at this point, and we're going to follow that here to a new point, and that's going to give us this point x1. Right, and so what is this linearization? So we're going to write L of x is equal to, and let's just put this in, say, what, point slope form. So it's f prime at x naught times x minus x naught plus f at x naught. Okay, and so so then we find x1 is whatever the root is of L, and that is going to be minus f of x naught divided by f prime at x naught, and then plus x naught. And so in general, we're going to have the equation of x of n plus 1 is equal to x of n plus minus f of x naught divided by f prime of x naught. And this is what is called Newton's method. And this will get us started. Okay, so let's take a look at a particular example. Here. Let's make this a little... Oh my god, I can't write right now. Alright, so example. Okay, so consider the function, say f of x is equal to x squared minus a for some a bigger than 0. So our goal is to find the square root of a, which makes f 0. Right, so f of root of a is equal to root of a squared minus a, and so that's 0. Right, but this might end up being an irrational number, so we can't just say plug in like 2 if a is equal to 4, because, okay, well in that case we can. But I mean, if we have 2 and we're trying to find square root of 2, then we don't know what to put in there without coming up with some sort of approximation. So what we're going to do instead is we're going to use Newton's method. If you take a look at Newton's method here, it's pretty interesting. So we're going to start with a guess. Say x naught, and if we'd like, maybe let x naught be greater than, say, a. So we know it'd be bigger than the square root of a. If a is bigger than 1, sorry. And then, so then what we do is we just go ahead and say, all right, well then in general, we have that fn should be, fn plus 1 should be equal to xn plus 1 should be equal to xn plus f of xn divided by f prime at xn, right? And so then we get xn plus 2xn, xn squared minus a divided by 2xn. Okay? Let's see. So we can combine these fractions together, and we end up getting 2xn squared divided by 2xn. And then we have, oh, and that should have been a minus. Ooh, sorry, my mistake. Minus here, minus here. Okay, there we go. And then we get what, minus xn squared plus a, and then that turns into, it looks like we're going to have xn squared plus a divided by 2xn, and if I pull out the 1/2 and I divide each of these terms, I get xn plus a over xn. And so this is the is actually Heron's formula for the square root. And so it was one of the first things we talked about in the class. And so we see that Newton's method actually reproduces exactly Heron's method for computing square roots, and we already know that that converges. But what we'd like to know is we'd like to know that there are some conditions in which we can guarantee that Newton's method will converge without all of the extra arguments that we made that were specific to this case. So in this case, we used algebraic geometric inequality, and that might be a tall order to ask for a general function and a general Newton sequence generated by Newton's method. So so why don't we go ahead and take a look at a proof. Okay, so we're going to go ahead and prove Newton's method, and just to write it down, xn plus 1 is equal to xn minus f prime at xn divided by f double prime at xn. Wait, no, that's not right. Is it? No, hold on. Hold on, maybe I should actually look at this thing. Yeah. F of xn over f prime of xn. There we go. Mental lapse. Anyway, I'm coming back to this like a day later, so it's not quite fresh in my head. But let's go ahead and talk about the convergence of this. And so what do I mean when I talk about convergence? Well, I'm trying to arrest the difference between xn plus 1 minus alpha. And so let's just do a sketch and see what this entails. If I expand xn plus 1, that becomes xn minus alpha minus f prime, f of xn divided by f prime of xn. And something I can do is I can factor out this term here, and I basically get the absolute value of xn minus alpha times 1 minus f of xn divided by xn minus alpha f prime of xn. So I factored it out, and since we now have a term on the second bit, we ended up putting in a denominator. So what can we do? Well, we're trying to figure out some way of getting this small. And if I continue following what you would do with algebra, basically find a common denominator, this is what will end up happening. So you get xn minus alpha. There's not really much else to do at this point. So we say it's going to be xn minus alpha times f prime at xn minus f of xn divided by xn minus alpha times f prime of xn. Okay, nothing complicated yet. But something else I can do, and this is interesting, is that I can subtract off f of alpha. We're basically making the assumption that we're looking for a root, and so we're saying that f alpha should be 0, so we're looking for alpha, right? And so if I subtract it, we're not actually changing anything, because, well, that's just 0. So that's all valid. But what this gives me, though, is it gives me the ability to use the mean value theorem here. Because it's basically a function at 2 different points, and so I get this. So we have xn minus alpha times xn minus alpha times f prime of xn. Well, maybe we should just move this to the next line. F prime of xn, and now we have f prime of cn times xn minus alpha, again, divided by xn minus alpha times f prime of xn. Okay, and this is for some c n that lies between xn and alpha, or the other way around. I'll just say between. No, okay. Xn minus alpha, or it's n alpha xn, depending if xn is bigger or smaller. You get the idea. So what do we do? Well, now I have xn minus alpha in all my terms, so I can go ahead and cancel them. So I'm left with xn minus alpha times f prime of xn minus f prime xcn divided by f prime of xn here. Okay, so that's nice. Now what? Well, again, I have a difference between the same function at two different endpoints, and so I use mean value theorem again. And so this is again equal to the absolute value of xn minus alpha times f prime of xn, or of, say, now some other term, eta n, times xn minus cn divided by f prime of xn. Oh, and that should be a double prime here because this was the first derivative. Okay, so we used mean value theorem twice, and now we're left with this. Now, because cn was between xn and alpha, that means that xn minus cn is smaller than xn minus alpha, so I get this. This is less than or equal to xn minus alpha squared times the absolute value of f double prime of eta n divided by f prime of xn. Okay, well, that's good. Here again, I should note, let's put this on the side, eta n is between xn and cn, or the other way around, depending on the order. So good. All right, so let's take a look at what we have. There's not much else we can do at this point. So we have this xn plus 1 minus alpha, so that is how close the next iterate will be, where we think of the current one as being xn. And so we have this relation here. So I'd like to show that the difference is getting smaller. If it's getting smaller, how can we demonstrate that? Well, I'm basically going to be looking for, basically we want, say, f double prime of eta n over f prime of xn, an absolute value to be less than 1. That would shrink it, definitely. And maybe even, we could even include xn minus alpha here and make all that less than 1, and then we still have a xn minus alpha left over. And so then we can show that each iteration, this chunk that we're looking at is making everything smaller. But we can't generally expect the second derivative to always be smaller than f prime in magnitude. And so this isn't always going to end up working. And we saw, and we're going to see later another example where we're going to end up having a cycle. So we basically want to restrict ourselves to a region where the second derivative doesn't change, it doesn't get bigger than the first derivative, and then we also need to choose xn minus alpha so that it also everything still stays small. And if we do that, then we can make this claim that we're actually going to end up getting smaller and smaller, and we're actually going to converge to alpha. So basically, the idea is that we just try to pick a point as close to alpha as we can in practice, but we'll get more precise about this in the theorem statement. Okay, so why don't we go ahead and make a formal statement, and this corresponds in the numerical analysis textbook that I've been following here. This corresponds to Theorem 4.61. We make a few minor adjustments because we had a factor of 2 that there's a factor of 2 that they have that we're missing, but then it looks like when they're actually assembling everything at the end, they have to cancel it out anyway. So we get the same result, but slightly different theorem statement. So what we're trying to do is basically trying to arrest the growth of that term with f double prime over f prime. And So we're basically going to establish a bound over this guy, and then we're going to put a requirement on how close we are to alpha to begin with in order to keep that term less than 1, this overall term. So we don't actually require that this be less than 1 as much as the whole combination be less than 1. All right, so let's take a look. So, I guess in numerical analysis. And yeah, okay. So what we're going to do is we're going to let alpha be a what's called a simple root of the equation f of x is equal to 0, and we're going to let I sub epsilon be given by this. So it's going to be x inside of the real numbers such that x minus alpha is less than or equal to epsilon. And so essentially, basically we have some alpha, and we're staying between alpha plus epsilon and alpha minus epsilon. And so wherever we put our x's, that's going to be our x. Okay, so we're there, and we're going to assume that f is, say, C2 over this interval. So it's twice differentiable over this interval I. All right, so we're going to define m of epsilon to be equal to the maximum value for s inside of I epsilon, and also t in I epsilon. So it's a maximum over two different quantities of f double prime over s of s divided by f prime of t. Now in the book they have a 2 down here. We don't have a 2, but ultimately the final statement ends up canceling everything out. So, all right, so that's what we have so far. So what does it mean to be a simple root? I haven't actually stated a conclusion yet, but before we jump into it. So if it's simple root, it basically means that f of alpha is equal to 0, but f prime of alpha is not equal to 0. And if we're twice continuously differentiable, then you can pick an epsilon small enough so that so that the second derivative is never 0 anywhere in this interval. So that means that this doesn't blow up to infinity. And we need to be able to define Newton's method over here, and if we have a 0 on the bottom, that's a big problem, right? So that's one thing we have. And now we also know why we need our function to be twice differentiable, and that came from the 2 uses of the mean value theorem, first here and then here. And so okay, so that's good. And now we want it continuous, and that facilitates using the extreme value theorem over this region. Okay, so that's where all those conditions come from. Okay, so now here's where epsilon comes into play. If epsilon is so small that epsilon times m epsilon is less than 1, then for every x naught in this interval, so if we start in this interval, Newton's method is well defined. And that's because if this was finite, then that means that this guy didn't blow up, and so that means we don't have any zeros in the derivative, and converges to the only root alpha in I epsilon. Oops. Too big of an eraser. There. Okay. So good. All right, so we have convergence. All right, so now let's talk about how we actually get the convergence. And so we're going to use the fact that we already sort of worked everything out here. So basically we'd have to run down to this, and we're going to extract this last bit and this bit and move on to the next slide. Okay, so what is that? How do we do this? So proof. All right, so we've already shown that xn plus 1 minus alpha is less than or equal to xn minus alpha squared times f double prime of eta n divided by f prime of xn and all in absolute values, right? That is where we left, if I'm not mistaken. Yep, cool. All right, and this is less than or equal to xn minus alpha squared times m epsilon, and that's by hypothesis. So we're assuming that m epsilon is finite. And to a couple other remarks. Let's see. I stated all this as we went, but yeah. So since f is a C2 over I epsilon, and m epsilon is finite, we have that f prime is non-zero in I epsilon. That's because m epsilon is finite. So xn plus 1 is equal to xn minus f at xn divided by f prime of xn is well defined. Right? So we have that statement. Okay. So at this point, we are going to try to show that this term on the right is basically going to be something that's going to smash down and make this guy go to 0 as n goes to infinity. Right. And so the way that we do that is this. So we start with, so basically consider x naught, which started in I epsilon. X naught started in I epsilon means that x naught minus alpha is less than epsilon. That is the definition of what it means to be in I epsilon. And so then we see then that, say, x1 minus alpha is going to be less than or equal to x naught minus alpha squared times m epsilon. And this is less than or equal to x naught minus alpha times epsilon times m epsilon. And so this is less than or equal to x naught minus alpha, which is less than an epsilon. And so then we see that by induction, we have that xn minus alpha is less than epsilon for all xn, for all n. So as we keep iterating this, we are going to stay within this interval, and so we have that going for us. So what you can do then is the following. So you start off with xn plus 1 minus alpha, and we know that this is less than or equal to xn minus alpha squared times m epsilon. Well, shave off one of those terms, and this is less than or equal to xn minus alpha times epsilon times m epsilon. And so now we know that this is less than epsilon. So then we can keep iterating this, and then we get this. So we get this is xn minus 1 minus alpha squared times m epsilon times this term that came from the last one here. So we keep reusing this quantity, and now we went from xn plus 1 to xn, and now from xn to xn minus 1, and each time we pick up an extra square out of it. So then we can take this, and we get this is less than or equal to, say, xn minus 1 minus alpha times epsilon times m epsilon, right? So shaving off one of these guys, and now this is term squared. Okay. So we can keep this going, and so we've gone from n plus 1, and we went down by 2, and now we have a quadratic exponent, and so we can keep this going until we get down to to x naught. So it goes down to x naught minus alpha times epsilon to the m epsilon, and now we need to figure out how many to put in there. I believe this is n plus 1. So we go down by 1, and we gain this to the first power, and yeah, so we go down by n plus 1, and we gain n plus 1 power. Okay, great. But the big thing, this is less than 1 in absolute value. So what does that tell us? Is that this goes to 0 as n goes to infinity, and thus xn plus 1 minus alpha also goes to 0. And so we have proved the theorem. So that's a nice little result. And this looks like a, yeah, so that looks like everything. Okay, so before we depart, I should really go in and talk to you about at least one counterexample where we have sort of this cycle thing that ends up happening, because for any good user of numerical analysis, you need to know where it can fail. Okay, so example 1, or we'll call this problems with Newton's method. Okay, so here's the big kicker. So let's take a look at something really simple, and this is f of x is equal to sine of x, where we're requiring that the absolute value of x be less than or equal to, or less than 1 over 2 times pi, or pi over 2. We know what that looks like. I mean, from trigonometry and calculus, we've dealt with this like every day. So this is going to be pi over 2, and this is, say, minus pi over 2, and so that's the interval that we care about. And yeah, this is what sine looks like there, right? So it's flat up here, and it's flat down here, and yeah, and that is our root. So one root at x equals 0, and it is simple. And that's because cosine is a derivative, and cosine is 1 there. So if we try to use Newton's method, what is Newton's method? Xn plus 1 is equal to xn minus sine of xn divided by the derivative of sine at xn. And so this is equal to xn minus tangent of xn. Now, if we choose a point to start, and so if we suppose that x naught is selected as this x star, where basically tangent of x star is equal to 2 times x star, and so basically we're looking for the intersection of the line of y equals 2x and tangent, and there is some point where they intersect before they hit pi over 2, because tangent blows up to infinity, and at least for a small interval, y equals 2x is going to be bigger than tangent of x, so you know just by the intermediate value theorem they have to intersect somewhere. And so so we know that that happens somewhere, and so we'll just say x star is that point that we get through the intermediate value theorem. And then what do we find? Well, that means that tangent, x1 then is going to be x star minus tangent at x star. And that is going to be x star minus 2 x star, which is minus x star. Okay, then what is x2? Well, x2 would then, so x2 would just be x1 minus tangent at x1. But tangent at x1 is minus x star, and x1 is minus x star, and tangent of x1 is tangent of minus x star, which is the same as tangent of x star times a -1, because it's an odd function. Right? Well, that's going to leave us with minus x star plus 2 x star, and that gets us back to x star. But that was actually equal to x0. And so we end up having the cycle where we are going to go from, say, x0 to x1 to x0 to x1 to x0, etc. And so this will not converge. And so what went wrong? Well, basically, we didn't choose epsilon small enough. I mean, certainly f is twice differentiable, continuously differentiable, and so then there is, we will have somewhere on this interval, we can get some sort of bound on the second derivative over the first derivative, that m epsilon is going to be bounded, but f prime takes infinity here and here. And so that gives us some sort of clue of what will go on. But even still, I mean, if we shrink this just a little bit here and here, we're still going to end up having this x star falling inside that interval. And so that still won't help us. And so we just need to make sure that we stay, really close to there. And so basically, you need to have some good guess to start if you're going to land anywhere near the 0. And yeah, so that is one of the limitations of Newton's method. But sometimes that's all you got. In any case, all right, so we've gone through a couple of examples. So I showed you how you get Heron's formula from using Newton's method, and now we have this. I'll post a MATLAB at midnight video I made for my differential equations class, which shows you how you can use this to actually even solve integrals. Maybe if I remember, I'll even put a card up here, right here. Solve integrals, solve initial value problems. How to resolve implicit equations and implicit solutions to differential equations. That's what I'm talking about. Okay, sorry. I think I'm done lecturing for now. And we'll go back to the office. Okay, so that's Newton's method for solving nonlinear equations. And this is something we saw back in Calculus 1. There are a few things we saw. There's caveats, like sometimes there are cycles and loops where you won't actually converge. And other times it works out fairly cleanly. In fact, when we saw that if we're trying to find the square root of a number, we can use Newton's method on, say, x squared minus that number. And we saw that when we use Newton's method there, it actually boils down to just Heron's method, which we already proved converged. And then after that, we went ahead and we tried to find conditions that will give us convergence in more general cases. And so basically what we saw is that the error between xn and alpha and say the previous iteration xn minus 1 and alpha, it's going to basically shrinking by some sort of constant multiple that is less than 1, if you're inside the right interval. If you're outside of the interval, there's no guarantees. You might get local convergence in some other point, or you might find a different 0. But if you stay within this sort of range and you meet a variety of conditions on the second derivative and first derivative, then you're golden. And so, yeah, so this is a nice little example of solving nonlinear equations. And so next we're going to talk about the secant method, and then also, if we have some time, the method of false position. But yeah, this is a good start, and I'll stop here.